All right, let me make another video solution. Here's one from chapter 20, number 30, and I'll just read it. It says, 1 mole of an ideal gas does 3,000 joules on its surrounding as it expands isothermically to a final pressure of 1 atmosphere and a volume of 25 liters. Determine A, the initial volume, and B, the temperature of the gas. Okay, this one we've got some equations for, so maybe this isn't necessary to do a PV diagram, but that's always my go-to, and so I thought I would begin by saying, all right, I've got a PV diagram. And we have different processes. This one said we have a final volume, so this would be 25 liters, and a final pressure of 1 atmosphere. And since it said it was isothermal, it is a constant temperature, and that follows the shape of a hyperbola. I know that because for all gases, PV equals nRT. So if you have the temperature held constant here, mathematically that would be something that would, here's P, so here's the y-axis, here is then V, the x-axis, and that's equal to a constant. And that is your fundamental idea of a hyperbola that looks something like this. And if this was the x and y axis, or put another way, y would equal to some constant over x, and that's that hyperbola shape there. Okay, so not worrying about its shape, we're just going to call it an isotherm since it stands for constant temperature. And this is what it then would look like. And I guess it would start with a high pressure and a small volume, and it expands. Okay, and this one, like I said, we probably could get away without doing a PV diagram here, because we know this much is true: pressure, volume, and number of moles, and R and T. And at the end, they give us the pressure, and they give us the volume, and they've given us the number of moles. The only thing they don't give us is that temperature. And the temperature is a constant, so there's no point in calling it final temperature or initial temperature. So I'm just going to say, okay, 1 atmosphere, although I'm going to put it in as pascals, so 101,300 pascals, and a volume of, and it said 25 liters, but I'm going to put that as cubic meters, and then 1 mole, and then R is the 8.31 joules over a mole Kelvin, and then times the temperature. And as you can see, then a pascal and a cubic meter make a joule, and a mole cancels with that mole, and we're going to be left with temperature in units of Kelvin. And that is, you might argue, the final temperature, but it's a constant temperature, so it's also the initial temperature. Let's see, how did they even ask it? They said, what is, see, in B, they just say, what's the temperature of the gas? They don't say final or initial, as, again, probably best they don't, because there is no real change. I mean, there is no change to it, so there's no point in calling it initial or final. All right, so this is the pressure. This is the volume. Of course, if I then divide that by, 1, and then divide that by 8.31, I get a temperature of 304.7. So 304.7 Kelvin, or perhaps in degrees Celsius, whichever you want. It's about a 31 point, actually it rounds up, 31.8 degrees Celsius. But they don't really give us any units at the beginning, so I can pick whichever one I want there. So I guess I'll go Kelvin with that. So that's the Kelvin one. Now, the other one is the work being done, and the work is always negative the integral of P dV. Now, for this particular case, as you can see up here in the PV diagram, the pressure and the volume are changing. But the temperature is not. And so the key to doing this type of processes when calculating the work is to, change pressure into an equation involving volume. And we do that again with the ideal gas law. So this could be written as nRT over V dV. And then, of course, recognizing that the temperature is a constant, and then obviously the number of moles in R is a constant, we just have an integral of dV over V, which comes out then to be a natural log. And if we do it from some initial volume to some final volume, we would have log of final over log of initial. Okay? And then you can see we're ready to kind of plug this in and get an answer. We know that the number of moles is 1. We know as R is 8.31. The temperature, whether you want to call it initial or final, doesn't really matter. We've already figured that to be 304.8. And then we have the ratio of the initial over the final. Let me hold off because I'm going to talk to you about units here. But the other thing to put in here is they say 3,000 joules. So I'll put a little J there for joules. But I do need to throw a negative sign in here. Don't overlook that because they say 1 mole of an ideal gas does 3,000 joules of work on its surroundings. So the energy is leaving the gas. And so when energy leaves the gas, it's negative. And of course, it matches that negative on the other side, and that's perfect. Now, I thought I would say something a little bit about maybe the units here. Remember that this would be moles here. This would be joules, mole, Kelvin, and this would be Kelvin. And as you can see, and rightfully so, all the units would cancel off. There isn't any units. Of course, what that means then is what we're looking for is initial volume. It would have the same units that you put up here for the final. And that gives us an option of leaving the final volume in liters as opposed to converting it to cubic meters like we did before up here and doing joules. So I'm going to take advantage of that and just do something like this, noticing that the two negatives cancel off, and I'll take my 3,000. I'll divide that by the 1. I will divide that by the 8.31. I will divide that by the 304.8, and I get a 1.18. So I'll just put 44. Equals then to the natural log of final volume over initial volume. And now, getting rid of the natural log by raising it to a power of E, I get 3.27 as the final ratio of the final volume to the initial. Or putting another way, the initial is actually the final volume divided by 3.27. And now I can pick whatever units I want, and I'll go ahead and stick with the units of liters. So it's 25 liters divided by 3.27. And so 25 divided by that last answer is about a 7.65 liters. And I'll finish the answer in units of liters. Yeah, hope that helped.